Good evening, everyone. Today is an excellent day to study some real analysis, so we will go with some properties about the oscillation of bounded functions. These functions will be in particular scalar fields. So let's start with a little theory. We need to recall what is an oscillation. So to begin with, we start with these definitions. Let X be an arbitrary subset of Rm and f defined on this set. It is a real function with vector values, also known as a scalar field, and this is a bounded function. So we can define the oscillation of f on the whole set on its whole complete domain as the supremum of the difference between 2 points of its domain. So for any pair of points, we take that difference in which the absolute value of that difference to get that distance between them. So we can prove that this is also equal to the supremum of f of x, such that x is any point in the domain. Let me write it better. Minus the infimum of, once again, f of x and x in the domain. So this is a proposition that we will not prove here, but we can take it for granted. Alright, so this is the oscillation of a function. So from this oscillation, let me put it on. This is the oscillation of a function over its whole domain. So from here, we will want to study or to characterize what happens with the oscillation of the function, but on a single point. So what happens there? Well, we can define that first a function that we denote with this capital letter omega on some point of the domain. So let x be a point in the domain. Then we define this function that goes from the positive real numbers into the real numbers. And so we take a value here, and the result of this function evaluated here will be equal to the oscillation of f, but not on the whole x, but on a restriction. And let me put this a little to the left, so you get a bit more space. So this will be the intersection of v with a ball centered in x and with radius delta. So this is our positive delta. Now this particular function has some properties. Now first, this function is bounded. It is bounded because the function f is bounded. So since this is bounded, then the oscillation of the function is also bounded, because it is equal to the difference between the supremum and the infimum, and for a bounded functions, these two are real numbers. So the whole oscillation is a real number, and then this is the oscillation of the function, but on a smaller part of the domain. So this smaller part of the domain will have a less smaller oscillation than the function defined on the whole domain. So this function will have naturally an upper bound that will be the oscillation of f in the whole domain. This is bounded by that, and it is also bounded by 0. So on the left, it is bounded by 0 because if the function is constant, then naturally its oscillation will be 0 because the supremum will be that constant and the infimum also that constant, so that cancels out and renders out 0. So that function is bounded. It also has another property, and that is that, let me add another page, and that that other property is that, well, let me highlight this is the lower bound and this is the upper bound. So I didn't show in the screen. So there's that, and another property is that this function is a monotonous increasing function. So this is increasing, not strictly increasing probably, but increasing. So it can be like that. So that means that if we have two positive values, let's say delta sub 1 on delta 2, that holds that relation, then it will happen that omega of delta 1 is less or equal than omega of delta 2. And that is because this is equal to the oscillation of f in this smaller domain, and this, well, this other is yes, the same, but on that bigger domain. So just to remember some concept of real analysis, you need to recall that well, these are real numbers. So these are real numbers. So the following will make sense. So in the real line, if you have some bounded set, I'll just draw some values that this set takes on the real line. So if we take a subset of this set, well, this set has naturally it's an infimum and a supremum that are here. So if we take a subset, let's say we pick some elements here, then the infimum of this smaller set will be bigger, or at least bigger or equal than the infimum of the bigger set, and also the supremum will be probably smaller than that other. Could be a smaller or it could be equal. So given that the oscillation is the difference between these two elements, so the oscillation that could be, I don't know, could be this big, will shrink a little, probably, because it could remain the same, you know. If you take like the values that are here and here, then the supremum and the infimum stays the same. But at any rate, it could be a little, it could be smaller, right? It could be also equal, but it could also be smaller. So that explains why we write this symbol here. So that's by property of the real numbers. So we have that function, and it also happens that by the way that this function is defined, it follows that a 0 is an accumulation point to the right of its domain, because it is an open interval that has a 0 as a bound, as a lower bound. So 0 is an accumulation point to the right. So it makes sense, given that observation, it makes sense to write something like this. So this limit then can be defined because 0 is an accumulation point to the right, and this shall be equal to the infimum and why is that? Well, because as I told you, this function is increasing. So when we go to the left, I mean when we go to smaller positive deltas, then the function can only shrink. So this is that infimum, and well, by definition, this is the infimum of of this set, right? So that's a proper definition of a real number. This is an infimum, it's a real number also, and it's that limit here. All right, so we can define then the oscillation, the punctual of oscillation. Let me write it here. The oscillation of the function f in a point. So given that this function is bounded, well, this is here. So how will we define that punctual oscillation? Well, it will be you're seeing on screen. It will be like this, and we will denote this as the oscillation of f that on this point of the domain. So that's the definition that we will handle from now on. This also has some properties that are that can be easily understood. And the first property is that this punctual oscillation is bigger. Well, I think we have it in. Yeah. So let's go with a theorem. Not with that we introduce this definition. Let's go with a theorem. I was getting a bit ahead of me. So we have that oscillation, that punctual oscillation here, and this function satisfies the following properties. The first property tells you that the function cannot be negative. So that property can be easily proven because it happens that this value here is it is non-negative. So since 0 it's a lower bound of this set here that we can call this set as A, then 0 is a lower bound. So since this is the infimum, it will be bigger or equal than any lower bound. So that property holds. The next property is a little less trivial. It tells you another characterization of continuity in a point. So a function will be continuous in a point. A function that is a bounded scalar field will be continuous on a point if and only if its punctual oscillation on that point is equal to 0. So let's make some space to prove that property here. So we will prove that so we have two possibilities here, and the first is that, so let me write it here. The first case is that this x naught is an isolated point of its domain x. So if x naught is an isolated point of x, then it will be automatically continuous. So this will happen, and it will also happen that the oscillation here will be 0. And why is that? Well, because by definition, since this is an isolated point, then there will exist some delta positive such that this ball that with centering x naught intersected with the domain is equal to just x naught. So this is an isolated point. So when you get that delta, let's call it delta naught. So when you get that delta naught, then the oscillation of f on this here will be equal to the oscillation of f on these singletons, and this is 0, as you can check that this is 0. So we can say that this trivial implies that, and just because in the first case of x being an isolated point. So then we have another case which is less trivial, in which x naught is an accumulation point. So in accumulation points, the function may or may not be continuous. So now let's assume, or let's suppose that f is continuous in x naught. For the previous case, this go both ways, you know. So being an isolated point, I mean, makes both situations happen at the same time. So there is really nothing to prove there. So now let's suppose in this other case that f is continuous on x 0. Then it will follow that by definition of the limit, it will hold that for any epsilon bigger than 0, there exists some delta bigger than positive, such that for any in the domain, well, for any, let's say y in the domain, if x naught minus y is smaller than delta, then let me put it like that, then so we can make a little graph here just to clear things up. So this is x naught, and we say that if y is in this ball, then the distance between f of y and f of x naught is smaller than epsilon. So we can say that if we take another point here, y hat, then what will happen with the distance between these two elements? So it will probably be bigger than delta, but if that happens, then we may as well take, you know, divided by 2. And if we do that, then the distance between these y and y hat will be smaller than delta. So if that happens, then minus will be smaller than epsilon. So that means that for any epsilon bigger than 0, we can still find some delta which is this one, such that the distance between the function or the evaluation of the function in this ball is smaller than epsilon. So the oscillation of f on this ball, what will happen with this? It will be smaller than epsilon. Is that true? Well, I think it is, because this is this is a bound of for this well, it will be like that. This is a bound for these differences, and as we recall, that oscillation is equal to the supremum. So given that this is an upper bound and this is a supremum, it will hold that this inequality will hold. So what we want to prove is that the punctual oscillation is equal to 0, and recalling the definition, the punctual oscillation is the infimum. So if we put it in the real line, we want to say that this is 0, but we found that this oscillation is between these in this interval here between 0 and this epsilon. And what we should do to prove that this is the infimum of the set of all of these elements. So to prove that, we will need to first prove that 0 is a lower bound of this set, which is trivially true. We saw that earlier. And then we also need to prove that it is the bigger lower bound that there could be. So if we add some value to 0, then this new number will no longer be a lower bound of this set. But for any value, let's say epsilon hat, we can find a value of epsilon that it is equal to epsilon hat divided by 2. And so since there is, we show that there is a value here that is in this interval and epsilon hat is here, then this epsilon hat is not a lower bound. So this is not a lower bound. Then it follows that 0 is the bigger lower bound that there could be, and that is the definition of infimum. So it follows that 0 is the infimum of the set of all of those oscillations. And that infimum is defined, as we see previously, as the punctual oscillation. So that proves that implication. And now let's suppose that the punctual oscillation is equal to 0, and we shall prove that f is continuous in 0. So to do that, it follows it's kind of the same, because if 0 is the oscillation, the punctual oscillation, then any epsilon positive is not a lower bound of the set of oscillations. So since this is not a lower bound of this set, then there will exist some delta positive such that is smaller than epsilon, and this was the supremum of let me add a page. Yeah, this is the supremums such that x and y are in this, x and y are in this domain intersected by this here. And so this is for any pair of elements of the domain, but x naught is an element of the domain, so it will hold that that the supremum, oh well, that this, so for any x in, or for any y, for any y here, intersected with this, but you know, we can just write it like that. This is equivalent to say that y is here, and it will follow that minus is this is smaller or equal than the supremum, which is this number, but it happens that the supremum is strictly smaller than epsilon. So there you have it. This means that the function f is continuous at x naught. So yeah, it was kind of the same proof. So we have shown this, and now we want to prove that third property. If x is an interior point and this holds, then this happens. Well, this is, we can do it here in this little space here. So if x is an interior point of y, then there exists some delta such that it's like that, right? And so you know that this is the infimum of the set of oscillations, so this will be less or equal than, right? And this is equal to this because y is a subset of x. So this is a subset of x. This intersection is equal to this. And since this is inside of y, and then this will be smaller than the oscillation in y. And the reason for this this loss inequality is, you know, what I told you previously, this property of real numbers here. So y is this bigger set, and this ball here is the smaller set. So the oscillation shall naturally be smaller here than on the whole bigger set. So yeah, that proves the third property. For the fourth property, let's say what we have here, that the oscillation, the punctual oscillation is smaller than some positive constant, then there shall exist some positive delta such that the oscillation, the punctual oscillations is of any point in some neighborhood of x naught is smaller than that same constant. So let's prove it here. You know, the page. This is interesting. So let's go with a drawing. Let's draw the real line just to order our ideas. So C is here. 0 is a bound of, you know, every oscillation. So we have that the punctual oscillation of f in x naught is smaller than c. And so we want to find some neighborhood of x naught such that any punctual oscillation is still smaller than c. So let's go by definition. This oscillation is the infimum of these oscillations here. you know that. But then this, so if we go a little bigger than this here, let's say if we move up some epsilon small, we will find here some oscillation. Let's go with delta hat, and that is here. When this is strictly less than this value. So in this neighborhood, let's draw it here. We have x naught here, and this is this neighborhood, which is intersected with the whole domain X. So inside of this neighborhood, what happens if we pick any point here? What happens if we pick some X here? Of course, inside of X, right? So the distance between these two can be, we know that this is smaller than delta hat, right? So we can always, and this is a property of real analysis, of basic real analysis, we can always find a ball that is inside that bigger ball. So we can call that delta prime. And for delta prime, we can take the minimum of, this is the distance, so we could go by this epsilon divided by 2, and then we need to know what's the distance between X and the boundary of the ball, which is the delta, let me put it here. This is delta minus this value, right? So if we divide this once again by 2, and let's call this, I don't know, R. Then if we take the minimum of these two values, then this ball will be inside of that other ball. So as this ball is inside of that ball, then it will happen that is smaller than that, because because it is a subset of that other set, right? So this will happen, and then that, oh wait a minute, all right, so this is it is getting a little disorganized, but the thing is that let me write here this oscillation is smaller than that other oscillation, and that oscillation was strictly, and let me highlight that, strictly smaller than right, and that value was still strictly smaller than C, right? And so if this is some value of an oscillation in here in this point, and X is a point inside of this we choose that this is any point. So this happens, and then this is bigger than the infimum of f in that point. This is the infimum of all of these oscillations, so it will naturally be smaller than those values here. And so we have proven that for any x in this neighborhood, it holds that is smaller than c. And this is exactly what we wanted to prove. So that takes care of the fourth property. And last but not least, the fifth property tells us that if the domain is closed or compact, then this set here is also closed or compact for every non-negative c. So let's analyze that here. All right. A way to prove that this set is closed is by showing that that this set is open. You know, because this is the complement of this set. These are complements. So if this is open, then that complement is closed. And so why will this set be open? Why will that be? Well, because if you take any point for any, let's call this set A. So for any x node inside of A, we can always find some neighborhood. I wonder if that is possible. Is there? Can we find that neighborhood? And that ball that is inside of A? Will that be possible? Well, we already know that by the fourth property, for any point, so if x node is a point in A, then wait a minute, yeah, then the punctual oscillation in x node is smaller than c, and so we can find some delta such that for any point here, or for any y, let's say y, for any y here, it follows that the oscillation is smaller than c, and so it will follow that y is a point of A, right? So that will show show that this is a subset of A. So let me delete this, and this implies that it's a subset of A, which is also a subset of X. But what we need to prove is not this, but so we have that, this is true, but we need to show that this is inside of A. Oh well, some other, probably other delta. So to do this, we need to use that other property that we haven't touched, is that the whole X is closed. So we haven't used that property until now, so it's a good moment to do it. And since X is closed, then we may as well use some topology, so let's forget about this. then this implies that A is open relative to X. So it is not open that open. I mean relative to the whole space, but open relative to X. So the complement of A is closed relative to X. So if the complement of A is that, then let me add a page. So let's now reinvent general topology. And since this happens, then this is equal to some closed set intersected with X. And this is closed. But it happens that X is closed. So this is the intersection of two closed sets, which is closed. So the complement of A is closed, and that complement was that set, so this is closed. And if X is also compact, and that means it's closed and bounded, then this is a this is a subset of X, so it will also be bounded and it will be compact. So that's the reason this is a fairly nice argument of general topology, and that will conclude our final proof. So if you found this video interesting, please subscribe and leave a thumbs up and perhaps a comment, and also if you think that some part of this video wasn't totally clear, or if you want to add some more comments, some more information, you can do that in the comments down below, and I will try to read all of the comments. And so this will be it for today, and see you around.